Hello, guys. Welcome to another episode of CUDA Education. Today, we are going deeper into the topic of the depth pyramid and the near, near plane and far plane. So, actually, let us just run our application. This is the modern renderer application. You could Google metal sample code and then go to the metal sample code page, and you would basically be able to download this application and run it on your machine, assuming you have already downloaded Xcode. So basically you download the modern renderer application, double click it, you run it in Xcode, and you would basically see this. There's a minor hiccup where you might have to change a setting to, instead of run remotely, you sign in locally or something. It's just one little hiccup. But basically, when you double click the file, you should be able to run it in Xcode. Xcode is the programming interface used in the Apple ecosystem to program stuff. Okay, so it's sort of like your Visual Studio on the Windows side. Okay, but anyway, so this is our application, and we are talking about, we're continuing to talk about the depth stuff. I feel that we needed to spend more time on it, but one of the things that we are interested in is saving processing. So the things further down the road that we're not too interested in, that's farther away from the camera, we don't render in much detail. But the things closer to us, we do render in detail because it is literally closer to us. So it's subject to more inspection, and that's what we care about. That's what our attention is focused on, and that's what we do. So the things closest to us, we render in detail, and the things farther away, we don't. We also have to deal with figuring out depth testing, figuring out whether this plant is in front of that plant. And if this is in front, we just render this and we save on rendering everything behind it. Okay, so we just render this and we don't render the things behind it. Okay, but that's sort of the depth testing, depth pyramid, near plane, far plane stuff. So what I figured we'd do is just spend a little bit more time on that topic. We have our depth pyramid. So we have the things that are farther away and then things that are closer to us. So the farthest, background, lighter, less contrast, and more faded details. Mid, background, slightly more contrast and detail. Midground, clearer detail, stronger contrast. Foreground, sharp, detailed, darker, and near foreground. Closest elements, darkest, most detailed. So that is sort of the depth pyramid. And again, the idea, guys, is that we're trying to save processing for the farthest things, know what's closest to us, and then also, help us to figure out, just the depth of things, like where do things stand in the scene, okay? Then we have our near plane and our far plane. So the near plane is basically the closest visible surface in a 3D space, okay? Anything closer than the near plane will be clipped and not rendered, okay? So basically we have our near plane, which is the start of our register. We don't register things closer than the near plane. So basically this gap between the camera and the near plane, we disregard all objects, anything, any rendering, anything that happens between here and here, we disregard because we don't care about, this is where we set our near plane as. Conversely, on the far plane, anything beyond the far plane will be clipped and not rendered. So we set our far plane, the farthest visible surface in a 3D scene. So this is our far plane. And anything after the far plane, we also disregard. Okay. So now there is a thing where if you set the near plane too close to the camera, literally the camera will basically intersect or block itself. So basically, like if you set the near plane here, the camera itself would kind of be like blocking itself, and you won't see anything on the screen because it's too close to the camera, right? So there has to be some level of distance between the two, and and then we start registering things. So we're gonna say that the depth pyramid sort of lives inside of that space between the near plane and the far plane, right? So for obvious reasons, right? We only care about things that are being rendered, and what have you. So this is sort of depth pyramid, near plane and far plane. Now I'm gonna show you a graphic eventually, but one thing we have to understand is that um, there's two coordinate systems going on. There is the depth values and the world space and things of that nature. So when we investigate the scene in terms of distances and depths and stuff, you're gonna have different units, right? And because we're dealing with like depth values and world space and everything in between. Now, one of the things that you have to understand is that the units in one world is not it's not a linear relationship between what's in one world and what's in another world, right? There is a difference between the two worlds, right? So there is like a mathematical relationship, but it's not one to one, and it's not a percentage, so it's not linear, okay? But anyway, let us go to the other image, which is the this guy. So we have a depth pyramid again, organizing elements in 3D space from near to far. Okay, so we have key edge. As objects go farther from the camera, they get smaller, have less detail, lower contrast, and often shift towards cooler colors. Okay, so far background, mid background, foreground. Similar depth increases from bottom near to far top, right? So we sort of have that cascade, if you will. And then here, near plane and far plane, defining the visible ranges in a 3D scene. So we have our camera, right? Sets the closest limit of visibility. Anything closer is not rendered. Helps with depth, precision, and performance. Far plane sets the farthest limit of visibility. Anything beyond is not rendered. Affects performance and depth buffer precision. So farthest distance objects are rendered. Closest distance objects are rendered for the near plane, right? So this is the visible range. Only objects between the near and the far planes are rendered. Properly setting near and far plane improves performance and reduces depth-related artifacts, right? So this is sort of, the battle that we're fighting with that, okay? So remember now I said, guys, that that we have we have these units and these coordinate systems and all of that have to deal with the actual numbers now of what's actually being done. So when we look at this, we're gonna see now we have our camera, near plane, far plane, but we have this depth. We have our projection frustum. So the projection frustum is like the box, right? But we have a depth buffer value of 0 to 1. But then we also have world space units that go from 0.1 to 100. Okay, and I probably have to do a better job of making a better graphic. But right, so the depth value is from 0 to 1, right? Depth value is from 0 to 1, right? But then the world space is from 0.1f to 100f, right? And there is a relationship between the two that we have to investigate, which I'm going to try and pull up here. Just give me 1 second. Right, so just give me 1 second. I'm trying to pull up a conversation I had that deals with that exact topic. So just give me 1 second. Okay. Right. Okay. So, this is the lay of the land, near plane, far plane. We have our camera, but then we have this line that goes from, point 1 F to 100 F. Okay. Um, it gets messy actually in our code. So in our code, we actually have, you see, we have the near plane at 0.1 F and the far plane at 100 F. Okay. But then the depth values are only from 0 to 1. Okay. Which, it gets a little messy. So, let us dive into that conversation here. So we have our chat GPT conversation here. It says, what is the difference between the depth value of 1.0 F and the 100 F on the far plane, right? So remember, guys, we had, we have 100 F on the far plane, but the depth value is 0 to 1, but we have 100 F on the far plane and 0.1 on the near plane, right? F, right? So we're trying to reconcile this and this and this and this, right? Two different coordinate systems. They're not linearly related, so this is not a percentage of this. So 0.9 of this, 0.9 of the depth value does not correspond to 90% of this range. It's two different relationships. So that is what we want to tackle with this conversation. What is the difference between the depth value of 1.0 F and the 100 F on the far plane? Great question. This confusion is very common because these two numbers live in different spaces. Short answer: 100 F, a world space distance, actual units in 3D scene. 1.0 F, a normalized depth buffer value after projection. Okay, so the depth buffer, I believe the depth buffer value is what deals, with trying to figure out what blocks what other object, what is in front of what other object, and deciding, do we render this object or not? Because if the object is blocked, we won't render it. Okay, so that's kind of what I believe the depth buffer conversation is about. Whereas the near plane and the far plane is just, what's an airplane and what's a far plane. So what's really going on? 100 F equals far plane distance, world space. Okay, so that is, let's not even use this one. Let's use this one. All right, so far plane, right? 100 F is the far plane, and then 0.1 F is the near plane. Okay, so 100 F is a far plane distance world space. This is part of the camera setup. Near plane is 0.1 F and far plane is 100 F. Meaning render everything between 0.1 units and 100 units away from the camera. The units is sort of whatever your application and coordinate system is. So the F doesn't really, it's just whatever units you decide, and then you project out from those units that you initially decide, right? So 0.1 units to 100 units. So 100 F is physical distance in a scene, meters, units, whatever your engine uses, okay? So that is, but we say, okay, 100 F, whatever the units is the farthest plane on the, in the scene, okay? So, it's the farthest distance in the scene that we will render objects, okay? So 1.0 F, which is the depth buffer value normalized, after projection, depth gets remapped to a range of 0 to 1, right? So near plane is 0 and far plane is 1. So if we go to our image again, near plane is 0 now and far plane is 1, right? Not a linear relationship between the two coordinates, but in the but where they're dealing with depth buffer things now. So we remap, we say, okay, we're going to throw out the 0.1 to 100 F, and we're going to go 0 here and 1 here. And that's it. Again, it's not a linear relationship between the two. Very important, okay? So after projection, depth gets remapped to 0 to 1 range. Near is 0, far plane is 1. Meaning this pixel is as far as possible within the visible range. So when we have 1.0 as a depth, we know this pixel is far as possible within the visible range. So 1.0f is not distance, it's a relative value used for depth testing. So there is where I'm talking about. We're dealing with depth testing now. We're trying to figure out, what's near, what's far. Do things block one, does one tree block the other tree? Does one wall block the other wall, or whatever is behind the wall, or whatever? So 1.0f is not distance, it's a relative value used for depth testing. Remember, guys, we have zero, we remapped everything to be 0 here and 1 here, and then we're trying to figure out relative value within the scene, right? Why the difference exists. The GPU compresses real distances into a normalized range so it can store depth efficiently, okay? And compare fragments for visibility, Z buffering, right? So this is where, do things block other things, all of that stuff. Compare fragments for visibility. This mapping is non-linear, especially in perspective projection, which is why most precision is near the camera. Far distances like the 100F gets less precision. Okay, so you could see here that the projection is not, it's not like a square box that, just goes consistently across the screen. There's actually like a projection. There's like a frustrum. It's like a box that gets wider as you go farther out, right? So it's not like simple math. It's sort of, you have to take into account the projection part of it. That it's you're projecting and you're seeing more things as you get farther out into the scene, right? You could kind of think of it as here where, you see stuff up close here, but you're seeing less things. But as you go farther out, you're seeing, like, you literally see the whole building, right? As you go farther out. But when you're right in front of something, you just see the wall, right? But here you see the wall and everything, right? So it gets, it's a different, it's not just simple. It's not a trivial thing. So anyway, the GPU compresses real distances into a normalized range so it can store depth efficiently, compare fragments for visibility, Z buffering. This mapping is nonlinear, especially in perspective projection, which is why most precision is near the camera. Far distances like 100F gets less precision, okay? So you guys understand that. Putting it together. So concept, near plane, far plane, depth at near, depth at far. So near plane is 0.1F, closest visible distance, right? This is the value in the near plane, far plane system. Far plane, 100F. Farthest visible distance. This is the distance in the farthest plane, right? But this is a different coordinate system than this guy. So depth at near plane, 0. Normalized depth. Depth at far plane, 1. Normalized depth. So this guy right here is, remember, we're remapping this whole conversation to 0 and 1. So whatever this is whatever it is. But we're saying, okay, we're going to remap everything. We're going to say the near plane is 0 and the far plane is 1. And then whatever happens in the middle is whatever happens in the middle. But we're going to, remap that range from 0 to 1 just to make life simple for us, to normalize everything, etc., etc. Just know that when you start getting into the middle of this stuff, ranges between 0 and 1, it doesn't necessarily map. It's not a linear relationship. It's not a one-to-one or a consistent relationship between when this value changes a percentage and what happens in this coordinate system. Okay? But we'll discuss that on a different day. But just know it's non-linear. It's not one-to-one. So you might go 10% here, but this changes by 25%, okay, in terms of distance. But we'll leave that alone for now. Intuition. Think of it like this. World space, object is 100 meters away. Depth buffer, object is at 1, max depth, right? So this 100 meters is this guy. Depth buffer, object is at 1. And that all it communicates. If you see depth buffer at 1, you just mean you're at the farthest possible distance from the camera that we are allowed to see, or that we will render as visible. Okay? Important, got you. Because of the nonlinear mapping, the difference between 0.1 and to 1 uses a lot of precision. The difference between 50 and 100 uses very little precision. I don't even want to go out on a limb here, because this is like math stuff where you kind of I guess you're dealing with decimals. So yeah, there's a lot of decimals here. Right. Difference between 0.1 and 1 is using a lot of the difference between 50 and 100 is using very little precision. That's why you're choosing a good near plane, not too small, is critical. That's why choosing a good near plane is critical. Yeah. This precision stuff, it's actually a very big deal, but yeah, we'll investigate that at a different time. Yeah, so if you want, I could show you. Right. So yeah, guys, this is what I wanted to really we're normalizing the range, right? So we're normalizing the range. And that's what we have, and that's pretty much it. That's pretty much it. So let us reinvestigate. We have our depth pyramid. We have our near plane, far plane. In the near plane conversation, um, we have 0.1 f, and far plane we have 100 f. But in the depth buffer conversation, or depth value conversation, this is 0, and over here the far plane is 1. Okay. And I just wanted to I wanted to I wanted to just revisit this topic, because yeah, I wanted to revisit this topic because I don't think it was fully clear. Okay. um and then this guy is a little bit confusing. Yeah, I won't even show it again because it's confusing. Okay. But that's that's it. So we set our near plane here, and we set our far plane here. I believe if I change the far plane, well, if I increase the near plane, so having said that, if I increase the far plane, um, uh, no, so let's not do that. Let's do let's just do this. No, that's not what I want. Let's just do 10. Right, so you see that the far plane now is a lot closer, right? So we've investigated this before in a previous episode, right? But we see that, the far plane now is, like, if we even do 5, we'll see that the far plane is obscured. Right, so like literally we're just seeing stuff right in front of the camera because our far plane is not. And notice it's kind of uneven too. Like you could see when we have it off to the side, we show we show the tree, but as we direct our camera close to it, we don't show it anymore. So that shows you that it's not it's not a simple thing, right? But yeah. So that's near plane and far plane. If we do 1, 2, let's say we do 2. Yeah, I don't know. Let's do 4, 3. Let's do 3. Yeah, so I guess, guys, you could see here where, like, we could even see on the near plane being clipped too. So I'm assuming that if I go 4 here, that space will get smaller. Yeah, so you see the space gets smaller now because we're clipping, we're discarding stuff, whatever. Anyway, let me get back to what was my original values, guys. You guys should know by now. Good job. That's your original values, right? So then when we run it again, we get back our scene. All right. So you guys learned something today, guys. We are closing in on the first quarter of 2026. We have a goal where we're gonna learn metal in 2026. So if you haven't jumped on the bandwagon, you got to jump on it now. You got to jump on it now. Learn Apple Metal, right? You got to jump on the bandwagon. So get started. I have a playlist. I have a playlist of shorts, Apple Metal shorts, and I have a playlist of long form videos. Just play it in the background. You could learn a lot just by listening, even if you're not looking at the screen. If you're commuting back and forth on the bus or the train, or however you get to work, you could learn a little computer graphics on the way. It's not gonna hurt you. So anyway, this is the conversation, guys. This is Cool Education, guys. Support the channel, please. If you know anyone in your community that is artistically inclined, tell them about this stuff. I want to see who's going to create the next Disney, who's going to create the next Pixar, who's going to create the next AAA video game, who's going to create the next enterprise, anything, enterprise level, creative asset, whatever. Who's going to create the next Avatar? Who's going to create the next Toy Story? All of that stuff. So I personally am not necessarily creatively inclined. I'm more of a techie, but I want to enable you guys that are creatively inclined to be able to create things on the screen. And also, you also have to understand, guys, that if you learn metal, you would also be able to start implementing stuff on Vision OS. So Vision OS is Apple's, the Apple Vision Pro and stuff, where you have the goggles. If you learn metal, you could basically run these applications in the Vision OS platform, and you could basically create 3D worlds, in the goggles and stuff, right? So you can't lose by learning Apple Metal. It's just a world of opportunity. So be the leader in your community. If you know anyone that's artistically inclined, or if you know anyone that's into technology and stuff, start learning this stuff and get together and dive into this stuff. I'm learning it and I'm carrying you along the process as I learn it myself. This is CUDA Education. Like, subscribe, share. Thank you guys for watching. Have a great day. Goodbye.